Hello everyone, Kodongane, the native god here. Right, let us look at this exercise based on resulting velocity so as to have an idea of how to tackle it or how to tackle such a scenario. Right, so let's first read the problem statement. An aircraft can fly at a velocity of 280 kilometers per hour with no wind interference. It must fly to an airport 275 kilometers north of its current position. A northwesterly wind with a velocity of 72 kilometers per hour is blowing, right? So as you should know by now, with resulting velocity, we from the problem statements we should be able to establish what of the given data relates to the three velocities that are important or that are crucial for resulting velocity. Those are VO, VW. Those two, remember, are the components of VR and VR itself. So we have three velocities that we look out for, right? Or in the data given, we look at what the data that has been, in terms of the data that has been given, what of it relates to the three velocities, VO, VW, and VR, right? Now, first statement is an aircraft can fly at a velocity of 280 kilometers per hour with no wind interference, right? So what we can take away from the first statement is that, from the first sentence is that you've been given a velocity, right? This velocity is relative to the wind. And as you should know by now, any velocity relative to the wind is VO. Right, so essentially here we have VO, the magnitude of VO, which is 280 kilometers per hour. Right, the direction hasn't been given. Right, so as far as VO, we've been given the magnitude of VO, but we haven't been given the direction. Right, that we are able to establish from the statement. Right, it must fly, right? It must fly to an airport 275 kilometers north of its current position, right? So the pilot essentially must end up directly north after flying a displacement of 275 kilometers, right? Remember, in one of the videos, I did explain that any information pertaining to the displacement as well as the direction of its displacement, right, relates to destination, and any information that relates to destination essentially relates to VR. So here, as far as VR, we do not necessarily have the magnitude of VR, but we have essentially been given its direction. So the magnitude we do not know, but the direction has been indicated as north. Right, so we have the direction of VR. Right, also as far as VR, we are also given the displacement. So S is equal to 275 kilometers. Right, and then they say, so as far as VR, we've been given its its destination or its direction, which is directly north, right? That we are able to tell from the statement, or we are able to establish from the statement based on the fact that we've been given information that relates to the pilot's destination, right? So a northwesterly wind with a velocity of 72 kilometers per hour is blowing, right? So here, as far as VW, we have both magnitude and direction. The magnitude is 72 kilometers per hour. As far as direction, right, now they said a northwesterly wind with a velocity of that. Now if you look at the perspective of the direction of the wind, right, they neither said this is coming from this direction or if this is headed in this direction, right? So in a way, the wind direction is ambiguous. And as you should know by now, that if the wind direction is ambiguous, then you perceive it as coming from this direction, right? So if the wind is coming from this direction, right? So remember, this is neither, or they neither stated if this direction is, if this wind vector is coming from this direction or going in this direction, right? If that is the case, you perceive the wind direction as coming from the given direction. So if the wind vector is coming from this direction and northwestern direction, it means that it is headed in a direction that is opposite the given direction. Right, so opposite of northwest is southeast. Right, so essentially this is excuse me, south 45 degrees east. Right, so that's the given information. Right, before we go to our calculations, let's first draw the schematic illustration of our given information. Right, so you draw your Cartesian plane. Right, now as far as VO, right, as far as VO, we have the magnitude of VO, but we don't have its direction. As far as VR, we have the direction of VR, right? VR is headed directly north, right? And then we also have VW. With VW, we have both the magnitude and the direction. Right, so as far as VW, we have both magnitude and direction. Right, so we can start drawing VW. Right, remember, the vector you draw first will depend on which information or which data or which of the vectors you have information for the most. Right, and in this case, that's VW. Right, I suppose you could also begin with VR, right, seeing that at least you have the direction of VR, right? But for the sake of getting used, or let me say, for the sake of, in fact, it doesn't really matter, right? I just prefer starting with the vector in which you have the most information for, right? Otherwise, it doesn't really matter if you start drawing, right, in this case, VR or VW, right? As long as the vector that you draw first, right, you have the direction thereof, right, you should be fine. So here I'm going to start with VW, right? VW is southeast, right? Southeast is in the fourth quadrant, right? Southeast is in the fourth quadrant, so it's somewhere here, right? That's headed in this direction. Right, remember it's south 45 degrees east, so this angle is 45 degrees. So if this is 45 degrees, it means that's 45 degrees as well. Right, so we have the direction of VW, we also have the direction of VR, right? VR is directly north. Right, so we know VR is headed in that direction. Right, so this is VR. And then we have VW, which is 72 kilometers per hour. Right, we have this. Right, and then to complete the triangle, we know that you simply have to draw a line that connects the two vectors that you've already drawn. right? That completes the triangle, right? Now you have to complete the vector diagram, right? Obviously using the triangle law. And as far as the triangle law, right, the components of VR, which is VW and VO, they must follow a head to tail direction, right? And then VR itself must follow a direction that opposes head to tail. So this being VO, if VO is going in this direction, if VW is going in this direction, for VO to follow a head to tail direction, right, it must head to this direction, right? And that completes essentially the vector diagram. So your vector diagram isn't complete, right, unless it has directions, right? Because like I said, with the vector diagram, we follow the triangle law in drawing the vector diagram, right? Bearing in mind or making certain that the components of VR, which is VW and VO, they follow a head to tail direction, and that VR opposes the direction of head to tail, right? Just like this one, right? So as far as the given information, this is what it tells, right? This is the schematic illustration, right? This is the story it tells as far as the schematic illustration of what has been given, right? And then of course, we need at least one angle here. And the angle that we can work out, remember we said that this angle here is 45 degrees. If that's 45, it means this is 45 as well. So we have 45 degrees from here to there, right? And of course, this here is 90 degrees. So 90 plus the 45 gives us 135, right? So this angle is 135 degrees, right? So then we can name this A, call it B, call it C. And this will be side A, this will be side C, this will be side B. Right? Now obviously you bear in mind that this is the angle that we have, right? And this angle is the 90 plus the 45, which is 135. Right? So essentially we have everything we need to be able to apply the cosine law or the sine law. Right? Now let's look at questions. 2.1.1, calculate the direction in which the aircraft must fly to get to the airport. That's 2.1.1. So 2.1.1. 2.1.1, calculate the direction in which the aircraft must fly to get to the airport. Right? So the direction that the aircraft must fly to get to the airport, that's the direction of VO. Right? That's the direction of VO. Now remember here that even if you didn't know that the direction they're looking for is for VO, you already have the direction of VW and you have the direction of VR. Right? So the only direction you do not have is the direction of VO. Right? But again, if you just using your intuition here, right? Also what you've learned before landing on this video, right? If you've been watching my content, is that whenever they ask you to calculate the velocity of the aircraft, right? It's always either the takeoff velocity or the velocity of the aircraft relative to the air, right? But my point is here, whenever they've asked us to calculate, or whenever they ask you to calculate a velocity related to the aircraft, right, it is always VO, right? Because VR is essentially the velocity of the aircraft relative to the ground, right? So if they want you to calculate VR, they will specify either by saying calculate the resultant velocity, or calculate the velocity of the aircraft if the scenario you're looking at involves an aircraft. They will say calculate the velocity of the aircraft relative to the ground. Right? Either way, though, VR is the velocity of the object you're looking at, be it a ship, boat, or aircraft, relative to the ground. Right? So remember that this here is VO. We are given the magnitude of VO. It's 280 kilometers per hour. Right. So when they say calculate the direction in which the aircraft must fly to get to the airport, right? Essentially, if you look at this practically now, right? If we look at this practically, let's put this here. Right there. Right, if we look at this practically, right, remember here, essentially, the vector that represents the aircraft is VO. Right, let me double this right. Okay, the vector that represents the aircraft, or how the aircraft is moving, leading up to it reaching its destination, is VO. Right, so VO, practically speaking, is in that direction. Right, if you look at our vector diagram, right, VO is headed in this direction. So then you have to ask yourself, right, you have to ask yourself which quadrant relates to the direction that VO is moving. Right, obviously it cannot be the first quadrant, neither can it be the third quadrant, nor the fourth quadrant. It can only be the second quadrant, looking at the direction of VO. Right, so practically speaking, right, if this is our starting point, which it is, right, when showing your, or when drawing your vectors on the Cartesian plane, you always assume that this is your starting point. Right, so VO representing the velocity of the aircraft, right, upon taking off or after taking off. Right, this we can then take as our starting point. So the aircraft is going to travel like that, and then because of this wind vector, right, because of the wind vector, right, the wind vector is going to push the aircraft, right, it is going to push the aircraft to a direction that is directly north. Right, so after flying 275 kilometers in displacement, right, after flying 275 kilometers in displacement, right, the aircraft would have been pushed back to course. Right, so meaningly, if this is our starting point, right, if we were to take off knowing that our destination is this point, which is directly north, if we simply take off and try to go, or try to fly directly north, the wind vector is going to essentially push us in that direction. Right, that is why the pilot has to counteract the wind and fly in this direction, right, knowing very well that the wind vector is going to push the plane back to course. Right, so essentially the direction that they're looking for is this one here. Right, so remember, with direction, right, you have to calculate the angle, and your angle must be, what is this? Your angle must be referenced from an axis, be it the x-axis or the y-axis. Right, now remember here, right, remember that here we do not have this. Right, essentially we don't have this. This is what we've drawn. This is our vector diagram. Right, but by bearing in mind that this is the practical way of doing things, right, this will then tell you which angle you must calculate. Right, now here, either you are going to calculate this angle or this angle. right? Remember, your angle must be referenced either from the x-axis or the y-axis. So we are going to calculate either this angle or this angle, right? This angle is referenced from the x-axis. This one is referenced from the y-axis, right? So of course, bearing that in mind, you then have to look at which of the two angles relate to one of the angles in our vector diagram, right? And of course, it will be this angle, right? This angle here alternates with this one. If you look closely, you have somewhat of a Z pattern here, and because on that Z pattern this line is parallel with this one, it means the angles formed, right, by the Z pattern are alternating angles, meaning that they are equal, right? So that is to say that we have to calculate this angle, so angle B. So once you have angle B, right, angle B is equal to the angle referenced from the y-axis, right? So this angle will essentially give us the direction of the plane, all right? So now you calculate your angle, right? So that is angle B, all right? You have to calculate angle B. Calculating angle B, right? So we want this angle, we have this one, right? So we can use the sine rule, right? Because we're looking for one angle, we have another angle, right? But remember, in using the sine rule, right, you must have, if you're looking for instance, if you're looking for this angle, we must have the side that represents this angle. So side B, we do have side B, right? And this is the other angle which we have, angle A. So we must have side A, which we do. So we are able to use the sine rule here. So using the sine rule, say sine B divided by side B is equal to sine A divided by side A, right? We are looking for angle B. So angle B is equal to arcsine of side B times sine A divided by side A, right? Now you substituting arcsine of, now we use this because we're going to have parentheses on the inside. Side B is 72, so you have 72 times sine A. Angle A, remember, is 135, right? The 135 we get by adding the 90 plus the 45, right? So that's 135 divided by side A. Side A is given here as the 280. So that's 280. And of course, you have to close this. Now, if you punch all this in your calculator, you should get 10,476 degrees, right? That is angle B. So by calculating angle B, once again, essentially we get the direction of flight. Remember, we said that this angle alternates with this one, and this angle is reference from the x-axis, I mean the y-axis, sorry. Right, so if you have angle B, you essentially have the angle traveled by the plane referenced from the y-axis, right? And the y-axis are north. The angle is 10,476 degrees. The quadrant, or based on the quadrant, right, it means we are headed west. So essentially, the direction of flight, you can then say, therefore, VO is 280 kilometers per hour. Direction of flight, right, remember this angle, right, is reference from the y-axis. So direction of flight will be north. The angle is 10,476 degrees, headed west, right? And the west, or the north and west, are based on the quadrant that vector VO is on, right? And of course, if you happened to calculate the angle reference from the x-axis, right? So if you happen to calculate, remember that this is equal to the angle reference from the y-axis. If you calculated the angle reference from the x-axis, right, that would be 90 minus this, which you would get 79,524 degrees, of which then you would say, right, if you calculated, or if you reference your angle from the x-axis, your direction would then be, because the angle is referenced from the x-axis, right, you would then have west first. So this would be west 79,524 degrees north, right? Let's say, or, right? And that is how you would approach such a question, right? So the direction here, right, if your angle is referenced from the y-axis, this is your direction. If your angle is referenced from the x-axis, this is the direction of flight, right? Hopefully that was clear. So now we are going to look at 2.1.2. 2.1.2 calculates the time the flight would take. So they want us to calculate the time, right, it takes the flight to get to its destination, right? And its destination is reached after flying 275 kilometers in displacement. So 2.1.2. 2.1.2, right? They want us to calculate the time it takes the flight, right? Now, time relates, so time, just like displacement, relates to the flight's destination, or the pilot's destination, right? And as such, it means we have to make use of VR in calculating the time. So in having to calculate either the time or displacement, right, both have to do with destination, and destination relates to VR. So in order to be able to calculate the time here, we need to have the magnitude of VR, right? So how are we going to calculate VR? So this is VR, right? In order to calculate VR, you can use the sine rule, right? But first you have to calculate that angle, because remember, right, in using the sine rule, you have to have the angle and the side that represents the angle. So we're looking for this side, so we must have the angle that represents that side, which is angle C, which is not a problem. Why? Because we already have this angle and we've just calculated that angle, right? So you calculate angle C, calculating angle C. All right, so angle C, all right, is going to be equal to 180 minus, remember, the 135 minus the angle we calculated, which is 10,476. Right, and the reason for this is, remember, the sum of angles in a triangle must add up to 180. Right, so punching this in your calculators, you should get 34,524 degrees. Right, that's this angle C. So once you have this angle, right, you also have this angle and this side. So now you can use the sine rule. Right, using the sine rule, remember, you have sine, let's say, because you're looking for the side, let's say you have looking for side C, so this divided by sine C is equal to side A divided by sine A. Right, and then of course to get side C, right, you must make side C the subject of the formula, so you get rid of this by multiplying by its both sides. Hence you end up with A times sine C divided by sine A. All right, and then this side A, remember, is 280. So 280 sine C, and sine angle C we just calculated and got the 34,524 divided by sine A. Sine A is 135. All right, remember, sine A, I mean angle A, is this angle here, which is 90 plus the 45, which is 135. Right, punching this in your calculators, you should get, now remember that this is side C, and side C represents VR, or the magnitude of VR. So this will be in kilometers per hour. So you should have gotten 224,422 kilometers per hour. Right, remember that this represents VR. All right, now we have VR and we have the displacement. Remember that VR is equal to S over T. Right, we have VR, we have S, we are looking for T. So it means we must make T the subject of the formula. Making T the subject of the formula, it means T, right, is equal to S divided by VR. Right, this is equal to, the displacement is 275 divided by VR, which we've just calculated and got 224,422. All right, now remember, this is in kilometers, this is in kilometers per hour. It means that the time will be in hours. All right, now punching this in your calculators, you should get 1,225 hours. Right, and this is how you would attempt such a question. Right, I trust that this was helpful. Right, like, subscribe to the channel, also hit the notification bell so that you don't miss any further content. Also share the content with your fellow students. Right, see you on the next one. Cheers.